Hey folks, Paul Abernathy here. Hey, we got a great one for you today. So we're actually doing a design, a pull calculation for a customer. And it's quite a unique one here because it's pretty long. And they had special reels put together for this in order to pull this long run. So we're going to see how long it is together. And what's interesting about this is that there are no pull boxes that are being added here. So it's simply pulling from point A to point B. They are not going to be exceeding 360 degrees of pull. We'll see. It's schedule 40 PVC, trade size 3, and it's got some elevation to it. It's got some incline. So those type of things we have to be aware of. All right. So we're gonna see how this is going to work out, and we're going to see. Now, I kind of have an isometric drawing. I don't know if you can see this. This kind of shows you kind of out the elevations. That's typically what we want for a drawing. We want to make sure that we know the elevations, everything that's involved in the actual layout so that we can do this calculation and that type of thing. I'm going to show you how we do quite a few of these things. Let's see here. Let me see if we can get some stuff together, and we'll do this together. I'll show you how I work this out when we're doing this, okay, so you can kind of see. All right. So first things first, let's go over into the program. So here we are into the program, and what we're going to do is we're going to create a project, right? And the first thing we're going to do is create a project, and this project is the Bills project, BILS. This is the Bills project. So we're going to go ahead and create a project. I'm going to call it the Bills project. Let me move my mic here so y'all can see me, hear me, but also get it out of the way so I can type. So this is, I'm going to call it the Bills project is what it's called. And basically all I'm going to do here is repeat what is in the actual pull. It is from panel board. That's what they told me. Panel board RT123 to panel board RT2456. Right. So, excuse me, 3456. Okay. So that is the pull. What it also constitutes is, in this case, it's 3-phase. So there's 3 500 KC mil copper, THHN. Okay. There you go. And then there is a neutral. So there's 1. And they say it's 250. So again, we're taking that straight from the engineer. That's what they said, so we're not going to get into recalculating that for them. That's not what the pull calc's about. Pull calc's about what they give us to calculate. And there is 1 equipment ground in there, and they say it's what 3 AWG copper THHN. Okay, so those are the conductors that we have in there. Okay, all right. Now we're going to have to build this out for these conductors to be pulled into this raceway. Okay, so again, we're going to save that as the project. All right, so here we're working in that project right here. So you see here's the Bills project right here. It's got everything that we put in the notes right here just to remind us right here. And a lot of times when we're working these, actually we'll put in here after the 500, 250, and 3, we'll actually put the values that we're going to get from the product sheet from the manufacturer so that it's kind of in there so we don't have to refer back to it and things like that. But we're going to actually go look those up and show you how to do that today. Okay, so now the first thing we've done here is put all this information. So now we need to build these conductors to be able to put in. So I'm going to go right up here with the cables. And of course, whether it says cables or conductors, it doesn't matter because we could build out an entire cable assembly if it's repetitive. Like if this was a repetitive assembly, we could build that out, or we could put individual conductors in here and then add them to the actual pull individually. So let's go to the cable. All right, so what we're going to do here is we're going to create a cable. All right, so I'm going to create a cable. And what we're going to do is we're going to call this, and we're going to call this, since this is very similar, we're going to do each of the 500s, the 250, and the 3 separately. Okay, so we're going to call this the 500 KC mil THHN copper. Okay, we're going to call it that. And we're going to call it by name. And I'm also going to use that as description. Same thing. We could put the cut sheet from the manufacturer on here so that it prints out with our report. We're going to be using Encore wire today. for this one. And the jacket type, in this case, there are going to be pulling a THHN, so it is a nylon. So here's your nylon right here. So we'll choose nylon. Now, what we have to do is find the OD for this actual 500 kcmil. So at that point, we have to go to the product sheet from the manufacturer. Now, you'll also notice that we have to find the weight as well per foot. Now, most of the time, the manufacturer is not going to give us the weight per foot. We have to calculate that out, but that's easy. We can calculate that out. That's a pretty easy process. So let's go here real quick and jump on over, and let's go to the manufacturer's product sheet. So this is the typical THHN cut sheet you can get from any of the manufacturers. Gives you some of the standards on it that they follow to make this conductor. And of course, it'll tell you the jacketing is again nylon covering, all that kind of stuff. PVC insulation, all that good stuff is here. What we want is down here in this, the information from the manufacturer. So we're doing 500, so that's right here. Okay. So this is the data here that we want. It's hard for you to see, so I'll scroll down. So this is the data we want. Now, what we really want, okay, is we want to find the OD. Okay, so I'm going to zoom in here, and let's see, OD column is right here. Outside, so we're going to come down. Remember, we highlighted 500, so that is it right there. So make a note, 0.902. So 0.902, that's your 500s. Okay. Now, while we're here, we're going to go and get that 250 as well. So that's right here. So we'll highlight 250, right? And then we'll find the column for OD right here, and we'll zoom in on it. Right here, so that's your 250. Here's the OD right here. So we'll come back down to that. Okay, so for the 250, it is 0.678. So that's your 250. Okay, and then while we're here, we might as well go in and get the 3. We want to be, good about our time when we're doing this. So we'll go back out and we'll go up here to 3. Here's 3. I'll highlight that out, and here's the column for the OD, and I'll come in here. And there's the OD, and it's 0.346. So 0.346, that's for the 3. Now, what else did we need? Now that we're here, we should have done that when we did the other one, is now we need the weight, okay? And so if you go up here, you'll look here, I'll just go here. So here's the approximate weight, and this is per 1,000 feet, okay? So we're still looking at the 3, right? If you remember, the 3 was 0.346, so that means that it was right here. Okay, well, we'll verify that. Okay, so here's the 3 column. We'll just keep this out, run this all the way out, and then we'll find the weight, approximate weights right here. So we'll zoom in on this one right here. All right, 189 pounds per 1,000 feet. Okay, so we need to find out what it is per foot, right? So 189 divided by 1,000 gives us 0.183. Okay, so it's 189. Okay, so that is the weight per 1,000 feet. Okay, now what we didn't do was get the same for the 250, so we might as well get that while we're here. So here's 250 right here, and we can see that weight here it is per 1,000 feet weight. So it is right here. So what it is 849. Okay, so we take that 849. Divide that by 1,000. That's going to tell us that the weight per foot is 0.849 for that 250. Right? We'll verify that. We'll zoom out. Follow this all the way over. And there you go. There's the 250. Right here. 250 right there. And there's the 849 right there. So we got that one. And the last one was 500, which we didn't grab. So I'll go and grab that now. So the 500 right here, it looks like that is 1,650 pounds per 1,000 feet. So obviously that would be 1.65 for per foot, but do 1,650 divided by 1,000. That is 1.65. So we're going to write that down. 1.65 pounds per foot. Okay, from that perspective, that's all you really need from the manufacturer's cut sheets. That's pretty much all that is necessary for that. So we're going to go back over to the worksheet. All right, so now we are building this first 500 right here. This is the first one, okay? So the OD on that 500 was 0.902. and the weight on that was 1.65. Now you can leave the side pressure blank, the maximum tension blank. All that will be taken up later when we do the calculation. So we're not worried too much about that. Okay. All right. So now I'll save that. Right, and now what we want to do is we're going to create another one here. So create another cable, and this one's going to be the 250 KC mill. And this is going to be THHN as well. So this is 250 KC mill copper. So it's going to do CU on it. All right, and we can recopy that, paste that for the description. That's fine. Manufacturer, we're going to put Encore wire so that we can build a kind of a base of just things that are Encore wire. These again are nylon, and now we can put in the weights for the 250. And so the weight for the diameter for 250 was 0.678. Oh, 0.678. And the weight on that was 0.849. 849. Okay, and we'll leave this other stuff blank right now. Click save. And then lastly, we want to go on and put in the third one, which is, this would be a 3 AWG THHN. We go copper. Okay. And we're going to take that, copy it. Description, we'll just paste that in there. Manufacturer again, Encore wire. Again, this is a nylon THHN covering. And then, of course, the OD on that one, if you remember, was 0.346. And the weight on that was 0.189. And again, we're leaving the max tension, all that. We can do that as we do the pull. Okay, so we're going to save that. So as you see, I've added 500 KC mills in here. I've added 3. I've added 250. And then typically we'll have a bunch of them in here. But you can also, as you can see, we can make an entire assembly that can go in here in just one if it's repetitive. We can do it that way. What we do is just add all the weights up, add everything up, and we can seriously do it that way. But we like to do these and create it this way so that we can add it individually to each raceway as we're working it out. All right, so now let's go back to the projects. Let's go back to our project. Okay, so now we want to work this out. So now that we've got everything set up, we're going to start this pull. Now, the engineer has told us that it's a trade size 3. We're going to see if that is okay. It said schedule 40. They gave us the conductors, that type of thing. Now, the engineer has also given us the coefficient of friction to use, but we're going to see what, and it is, they're using Polywater J pulling lubricant. So we'll see how that works out. So let's start this pull calculation and see for this engineering firm, see if we're right here. All right, let's start the pull. All right, first of all, let's name this one. We're going to call it the Bills pull calculation. All right, and this is a pull, and we're going to say that this is a 3-inch or trade size 3 PVC schedule 40 with, we'll put 3 500 KC mill copper, 1 250 KC mill copper, and 1 3 AWG copper. And of course, we'll do all THHN. All right, so that's just kind of a description of the pull. Now, also in here, many times we'll put certain disclaimers in here for the client. We might even put something in here, our own disclaimer in here. We might even put that this is from this panel to this panel, that type of thing. All that kind of stuff would be put in here. So, okay, so let's go next. Okay, now the next thing that we're going to look at is whether or not the run is, what's the size of the raceway. They gave us and said it was a trade size 3 PVC. Whether it's good, fair, or poor. If it's being reused, it might be a fair or even a poor if it's got some age on it. If it's a brand new installation, we're going to say it's good. One of the questions we're going to ask is the raceway being cleaned out? That type of thing. Is it a new raceway? Has it been pulled with the cleaner through it? Anything like that. Say a rabbit been pulled through or something in that scenario? They say yes, then we're going to put down what the engineer says, trade size 3, and we're going to say it's in good condition. And we're going to go to the next thing. All right, so we're going to add the cables. So now in this scenario, we know we have 500s, and we've got 3 of them. So it's going to go pretty quick at that point. So 3 of those. And then we add another cable. We know that we have a 250, and it's just 1 of those. And then we're going to add another cable. We know we have the 3. So there you go, from the drop-down list, we have 1 of those. You see why it was important to have all the information put in there? So this is going to give us our totals right here. Okay. And so that's the cables that we're working with in this application. So as you can see, there's 3, 4, 5 overall in this raceway. All right, now, this is where we're going to do the pulling lubricant. They want to use Polywater J, and it's a PVC raceway. And it's got nylon in it, and you see that the coefficient of friction, if you use the Polywater J, is 0.13 in here. And you can see it changes depending on the different, lubricants based on the different types of here. So if I was doing HDPE or I was doing XLPE type of a jacketed, but this is a nylon. So it's going to be 0.13 is what the coefficient of friction is going to be used here. So we'll click next. All right, next is arguably the most important part to me of a pull. And I asked the engineer, I said, what do you expect the back tension to be? And that is to get the reels running, get the reels moving. You don't want something that's so hard to move. So the tension is going to play a big role. Now, many times we will put in 25 or even 50 as a precautionary measure, even when the engineer says that there's 0 back tension, meaning that there's going to be some kind of pusher involved. Somebody's going to make sure the wheels start spinning so that it doesn't get herky-jerky. And so when the tugger's going, it's not going to cause that reel to have to, and the inertia from a dead stop. All those type of things. If there's something that reduces that back tension down to 0, that's really what we want. But we'll sometimes put a little protection factor in there. So in this case, I'm putting 50, and we can work from there. Now, maximum tension. Typically, I like to put the maximum tension on what the tugger is. All right. Now, a lot of times what we have to do is say, well, what's the maximum tension on the overall cable assembly? Well, we have to use a formula to get there. Since this is copper, okay, we would do 0.008 times the largest conductors that are here that are being utilized is the 500 kc mils. Okay, so we're going to use the 500 kc mils. So I'm just giving you an example here how I'll show it, and I'll show you the math. And times the number of those, there's 3 of those. And we're not even going to take into consideration the 250 or the 3 because they are smaller. So most of the pull and the tugging is going to be on those 500s, okay? So that's what we're going to kind of base our threshold on. And then I'll show you, because tuggers come in 5,000, 3,000, 10,000, that type of thing. So let me show you. So we're going to go 0.008 times 500,000 times 3 is 12,000, okay? So 12,000 tends to be the max tension on those 3 500s. Not taking into consideration the 250 or the 3, which becomes really relevant because most of the tugging is going to be on those 500s, to be honest with you. So that now, we like to build in what's called a safety factor and limit that to 75%, okay? So, but now, since the conductors can handle 12 and the tugger is maxing at 10, we still like to put a protection factor in here. So we'll take that 12,000, we'll multiply that. We'll go times 0.75, and that gives us 9,000, just shy of the tugger's max. So what we'll put in here is 9,000. Now, of course, we adjust these numbers depending on conditions. And, of course, sidewall pressure, we put 1,000. That's typically what you get for these sizes of thermoplastic or thermal set, that type of thing. Okay, so all of this information is in here. We're going with a very, 50 back tension. Fine. We maybe could remove that if that plays a bigger role or if we're really close, and we can mess with some of these numbers. But this is a very conservative way that we do our pull calculation the first go around, just to see where we're at. All right, so I'm going to save all that. Okay, so here we get a bit of a printout here. We kind of see what we got. So we've got 33.3% fill. So their raceway, they're fine at this point. Doesn't seem to be more than 40%. Okay, it's 33. That's fine. Trade size Say trade size 3 is what they wanted. Schedule 40 PVC, all that kind of stuff. That's what they wanted. All right. So we're going to start looking at this here and say, okay, this is what they chose. And that's the kind of raceway you choose. Oh, by the way, you can always go back in here and you can change these things, right? Coefficient of friction, polywater J, conduit type, PVC. You can change all these type of things, okay? Just in case you wondered. And here you see we're using a 0.13, all right? And all that kind of, so it's going to do the math for us and tell us how many jars or gallons they need of this pulling lubricant and all that as we go, all right? So we're okay. There's no jamming has been assessed because, again, this is a complex, means it's basically 4 or more type of conductors in there. So they're going to cradle out and complex out. So not an issue with jamming, right? And we're well within the fill, so we're okay here, right? 5 total conductors in there. All right, let's go on and start this thing. So remember what I told you about this pull? Basically, I've taken my notes, but basically you can see this kind of an isometric drawing, and we're going to kind of work this out segment by segment. Okay, so this is the way that they chose to want to pull it because of where everything is. Now, let me give you some advice here on this pull. If you look at this pull, they're actually loading the bends on the back end. First of all, it's not what I would recommend, okay? I would most certainly recommend you try to go through the bends the first part of this run, not have them 300 and 400 feet into the pull. So that's the first thing that concerns me. But we can always do a reverse review and see how I can recommend them to maybe do what they can do to pull it from the other way, or maybe even recommend that they put a junction box somewhere in a long span in order to break it down and make their pull a little easier. But let's see. Let's see if it passes the way that they want it pulled. All right, so we're going to add the first segment. Okay, so this first segment, it's going to be straight down. And from my notes that I have, it's going to be down. And it's going to be 12 feet of the straight portion, straight down. And it's going to end in a 90. That 90 is going to turn down. Okay, so we got to end it. So here it's going to end. And here it's vertically up. See, it's coming down and through. Right, down and through. So this is the one we want. Direction, again, it's coming down like this. You can't really see it. I'll move me so you can actually see these things now. I'll move me up here because you don't need to see this other stuff. All right, so you see here it's coming down. Okay, so this is downward pull, right? All right, and the radius of this, these are 3-foot radius 90s. So we've got that, and they're 90 degree. All right, and it'll already calculate the length of this and everything once we come over here and I click this. So we're going to, this one. Okay, so starting out, we have a negative tension as it goes into the raceway, and it comes out, we still have a negative tension. So we're good so far. We're coming down that first little segment. You see that 90 is 4.7 feet long. That is the overall length of that 90. The radius is a 3-foot radius. All of this comes from the manufacturers, so we ask for that stuff. And I'm going to show you how we do that ourselves here in a minute when we go look at the some data. All right, so that's the first one. So it ends in the 90. Now, from that 90, another segment. Now, this one is a slope, right? And it's a slope of 15 degrees, okay? So it's kind of a slope, and it's kind of an upward slope. Now, this is the thing that they were concerned about. It shows here that is 375 foot of slope. So between elbow to an elbow, it is 375 feet. That is a long pull. That's a lot of surface tension on this conductors, okay? Now, when it gets to that end, right, it looks like here it turns a 90 upwards, okay? So we're going to go here. It's going to have a bend, and it's going to end in a 90. And let's see the direction. It looks like here it's going to turn up right here. See it turning up? So we're going to go here. The radius is 3 feet for that one. And it's a 90. Okay, let's see what happens here. So there you go. It's still that. We're going to hit this. All right, so already going into that segment, there's 976 pounds of tension. Now, we haven't been, but I mean, that's a long run. And we're at 1,315 pounds of tension, okay? Well within our tugger's range, well within the wire's range. We're kind of monitoring it. We can change things as we go, but we're monitoring it. And the sidewall pressure is 307 at this point. So Seems okay on the sidewall pressure. All right, now, at this point, it looks like it's going to go up 25 feet to a 45. All right, so add another segment here. So again, this is a slope. Okay, so it looks like it's going to go up. No, it's up. Direction up. And it's going to be 25 feet, right? And it's going to end in a 45, right? So it's going to end in a still vertical up, right? So then we have a vertical down. So let's look in here and see. Okay, so direction, vertical up. Here it seems like it's coming up like this and not down, okay? And I just want to show you, if we were to have selected vertical down, by the way, show you here that this is vertical down, vertical down. So in this case, it is still a vertical up. Let's see. No, actually, it looks like the inner bend is facing down on this 945. Okay, so we're gonna say it's facing down, but the direction of the pull right here is up and through it. Okay, so it's not down, it's up and through. So we're gonna say up and through, right? And in this one here, they say that it is this 45. They're saying this is a 2 foot is what it is for this one. So we'll say it's 2 feet. And then we'll go to the angle. We'll say it's 45. And let's see what it gives us here. All right. So this tells us that this is a 1.65 foot 45. Okay. Again, you'll get all this from the manufacturer. Different raceway manufacturers will give you these published information that you can use, or the engineer will give it to you. Customer, remember, we asked for all this stuff, so it's an actual checklist. All right, so let's see how our, all right, we're at 1,695, okay. We're at 593 sidewall pressure, okay, that's fine. All right, so it went into that 45, well, ended into that 45, right? Okay, so it ended into that 45. And now another segment is going to be at a slope. And it's out of that 90, out of that 45, it's going to go 10 feet. Slope, direction, it's going to go up. And it looks like here it's 10 feet. Nope, I got that backwards here. Oh, and it is a 10 degree slope and 10 feet of that from that 90 as it goes out. So it went down 90, went up, 15 degrees for like 370 feet. Then it turned into a straight up 90, went up, ended in a 45. Okay, then out of that 45, it's going 10 degrees angle, okay, 10 degrees angle up into another 45, okay? So it's going 10 feet up, and it's going to end in another 45, okay? And so it looks like that here. And that one is also a 2, and that is also a 45, okay? So we're going to do that. Okay, let's see where we're at. We're at 19. Okay, not so bad. Sidewall pressure, not so bad. Not so bad. All right, so out of that 45, okay, so that 10-foot end in a 45. So out of that 45, it shows that it's going to go another segment. Now this one shows horizontal. So this one is horizontal. Okay, slope. Let's see here. Length for this one, it says 75 feet. Okay, and this ends in a 90, okay, and this looks like a vertical up 90, right, because the inside portion's aiming up, okay, so it's going up, and it's a 3 foot, okay, there we go, and the angle is a 90, got it, save, let's see how we're doing, okay, now we're up to 2,768. Okay, sidewall pressure is 646. It seems okay. Now the last segment is only 6 feet from the end of that 90 up to the box that they're pulling to. So that's the last segment. This one's going to be straight up, and the last is 6 feet. And there is no bend at the end because it's ending in the box. Okay, so let's check that. See where we're at. All right, so at the end of this pull, the engineer seems like he was feeling very confident about this. So it looks like it's 2803. Not a problem. That is nowhere near our Tugger's max. That is nowhere near the maximum that we set for the conductors. Remember, the conductors were 12,000 just based on the 500s. And so we also precautionary reduced that to 75%. Still nowhere near it in this pull. And then the sidewall pressure is well below 1,000 per foot. So this is a successful pull. Now, what's interesting on this pull is if they, they're asking us, is there any benefit to pulling this in the opposite direction? What's the reduction? Well, let's just show you all this sloping, what it does here. So here you see, let's write these down so we can compare. So it was, ending was 2803 and the sidewall pressure was 646, okay? Now, what if we reverse this? Oh, total bends. Total bends, 360, so we're in compliance with the code there. Total distance is 503 feet, still a long run. There's 17.3 feet of bend, and this total, that's the straight section, 503. Total length is a 520-foot run of 3 500s, a 250, and a 3 gauge in a Schedule 40 PVC. Okay, all right. Now, what about the reverse it? Let's reverse it real quick. If we reverse it, it's kind of interesting. If you look at how this reverse pull goes, look this out. Look at here. Actually, at the end, the sidewall pressure is 7 pounds per foot. Look how reduced it is. Tension is 30, ends at 103. That's it. From 2,803 and 646 sidewall pressure, just pulling this run in the opposite direction reduces it down to hardly nothing. There's zero risk. Now, why would this be a big deal, even though the other way would work? Well, if they could pull it this other direction, if it's a real sensitive location like a data center or something like that where they want to be extra careful, they don't want to put any risk, then they could do this one. And I'm be honest with you, they could reduce the size of their tugger. They may not need to use a 10K tugger. They might have used be a 5K tugger. They can get away with a 3K, something like that. Whereas the other one, you could have gotten away with a 3K, but put the maximum. Okay, it would be pushing that tugger here, right? So in this scenario right here, perfect. So that's the benefit of the reverse to look at it. And then you're going to make a recommendation. You're going to say, look, it'll work the way you want to pull it. But if you want to make your pull even easier for you, then pull it the other way. And they may say, well, I don't have the space to pull it the other way. I don't have the space to put the reels. I only have a place to pull it to. I can't start my pull there because I don't have the space for it. All right, well, that makes sense. So we looked at it both ways, and they're good to go either way, okay? So if we look back here at the original one, 2803 and 646 are all considered acceptable, okay? All right, and so then it's really easy to export the report for them, and the report will give all of this information in the report, and that's exactly how we would do it. So at the end of the day, that's a successful pull, and that was a long pull at 360 degrees worth of bends. It had a long 15-degree slope for about 375 feet. And then it hit the 90s at the end, and it still was okay. The reason it's so important some of these times on a pull is because you have somebody that looks at this, an engineer, as a design professional. Maybe you could only pull this way, and somebody might look at it and say, I don't like it because it's got too many bends at the end, right? Too many bends loaded up on the end. It's just not going to be successful. Well, we just did the pull, and it was successful. Okay, so that type of thing. So that's the importance. And now we can issue a certificate of accuracy for this pull based on the criteria that was given. So any deviation from that is something that needs to work out between the owner and the contractor in the engineering firm. All we did was certify the accuracy of this pull based on the information that was provided, and we will give you all that printout with their certificate, and you can give that to the electrical inspector, project manager, anybody else, and we verified that the raceway fill is okay. We verified that what the weights are, the manufacturer specific data is on there. That makes the owners happy that all that's on there. And then you're able to submit it. And that is based on a 0.13 coefficient of friction. Now, here's what a lot of times people say to us. Say, Paul, I'm using a different pulling lubricant. All right, so let's say the pulling lubricant is 0.17. Okay, then we're going to recalculate it out at 0.17 and go down and look at our calculation. So here's our calculation. Now it's changed to 0.17. Where does that change? Okay, big difference here is the fact that now it's 3,986. So you're not going to be getting away. Let me move me so you can see it. You're not going to be using a 3,000 pound tugger. Okay? You're going to be jumping up to at least a 5 or a 6 or a 10 or your standard 10. But your sidewall pressure is right there at the maximum. So in this case, if it was the coefficient of friction was 0.17 for whatever you were using, in this case, it's probably behooves you to really look at the reverse pull. Because even with this, if I go up and look at the reverse pull, with this increased side coefficient of friction, it's still just 8 pounds and 106 pounds of tension. That is nothing. So if I could pull it that direction, that's the way I would do it and not risk damaging these conductors at all. The other way, it's right on the threshold. Now, another question that people say, well, what if they cannot guarantee the back pressure at 50? What if it is 100? Okay, so let's show you what it would be at 100. So I'm going to click 100 at that elevated coefficient of friction of 0.17. And let's come down here and look at the math. Well, now the math pushes this thing to 4,000 pounds of tension, well within your normal tugger, the 5K or the 6K or even the 10K tugger. But your sidewall pressure still goes up to 931, okay? So again, but I want to show you how this can change. Let's go on and drop this. So what if they say, I guarantee you 0 back pressure? It means you're going to help this get started on the pull. Okay, you're going to have somebody there to get this roll so it doesn't have to go from a dry pull, dead pull, things like that. We're going to change this. We'll leave that at 0.17. Now you see that it tells you different types of how much lubricant you need. There'll be 4 gallons of it. But let's go down here now and see what we got. Okay, so if I left it and I remove the back tension to 0, then you'll see that that 50 really is not making that much of a difference. So that's why we use it as a fudge factor, because here's 3,986, okay, a little bit higher than it was before, a little bit higher, and now it's 922, that type of thing, okay? So now you can see why we build in some fudge factors in here. That's why I like to put something like a 50 in here, because now if you scroll down, you see that it's not a big difference, but it does have that set in there. Okay, anyway, and then you saw the benefits of doing the reverse pull, and we look at the raceways. Now, on this pull, if it had been too much, then we may have recommended in the layout, we might have said add a pull box so that it's accessible somewhere in that 375 foot, and closer possibly to where the bends start, that type of thing. And see, evaluate the installation and see if that would be beneficial or not. That's the kind of things that we do when we're doing a review of a pull calculation. But this one passed. So cool. Hopefully you got something out of it. This is kind of what we do. Now, if this was the same exact one for multiple sets, let's say it's parallel sets, and this was exactly how you do it, then it would be identical for each one of the pulls, okay? Because all of the criteria is exactly the same, that type of thing. Make sense? All right, folks, hopefully you got something out of that, kind of give you an idea of what it looks like to do a full pull calculation. This one that was submitted for the Bills project looks good. They can pull it either direction if they want. I just tell them make sure that they follow all the parameters if they're going to pull it as submitted, because they're getting really close to that sidewall pressure, not really close to the tension on the tugger or the tension on the conductors, but very close to that sidewall pressure. So I tell them just be careful, use plenty of lubricant, and make sure that you just be diligent for the pull. Make sure you follow your safety protocols, making sure the reels are clamped down, that nothing's going to move or chalked up properly, all those type of things, and you should be good to go. Okay, all right. Hopefully you got something out of it, folks. Take care.